Okay, so welcome all. Today we are going to be looking at following on from the previous presentation on chapter 10 of the book. We're going to look at chapter 11, exploring how visualizations can help us interpret predictive models. This chapter might be a little bit disjointed in the sense that it's the chapter has had some updates. So some of the graphs I'm going to show are from previous versions. So if you are following along or indeed can't remember a plot when you looked at the book, then it's probably just a timing thing. It's not a you thing. So we're going to look at how visualizations can give us insights in that just looking at summary statistics and black box model results might hide. The goal here is that we're aiming to make the features of the model and the kind of the way it fits the model visible and understandable, and also flag any issues with the modeling that we otherwise might not be aware of. So I'll talk a little bit about visualizing model fits for a while and why that's useful, and also a little bit about how some of these visualizations can be useful for communicating models to non-technical people. And then we'll look at a couple of example visualizations for that are useful in terms of model tuning or looking at deeper relationships in the data. Okay, so we'll start by looking at model fits. So, because the first question that arises is why should we plot model fits? So I think the key thing here is that whilst there are various statistics to measure model fits like mean squared error or R squared, and those are of course useful measures of how models fit data. But of course, like visualizing the predictions can give you a much more detailed picture. So if you like boil down the relationship just into one statistic, you are going to miss possibly some features of the data. So a famous example here is Anscombe's quartet. So this is a series of 4 small data sets with the same linear fit coefficients and indeed the same R squared value. But here you can see from the visualization that these are 4 fundamentally different different relationships between the predictor variable and on the X value and the predicted value on the Y value there. So I guess in the top left you can see that that's a linear fit is a reasonable case in the top left here. But in the top right, it's got more of I guess, a quadratic form or a curved form. And therefore, the linear fit might not be appropriate. In like the bottom left, we've got, it might be a linear fit, but we've got a big outlier there that might need to be investigated. And I guess a similar-ish story on the bottom right, where we've essentially got the linear fit being created by one value out here, and everything else is independently distant. The outcome is independent really of the predictor apart from that. So hopefully that shows you a little bit about why these things are valuable. Typically, of course, this is a very simple example. We're not going to look at one variable linear models, but I guess it illustrates the prediction here. If we're moving to kind of like more non-trivial examples, how can we look at the quality of the model fit? So one way to do that could be a predicted versus actual plot. That could be one of the first checks that you would want to use after fitting a model. So at its simplest, this could be a scatter plot, just plotting actual values versus predictions for your model. And this kind of plot can tell us, a lot about how well the model's doing. So Ideally, if you had like perfect prediction, you would want your points to be around this 45-degree line where the predicted outcome is close to the actual outcome. Of course, it's never going to be exactly all on the line. In fact, if it was all on the line, that's kind of, you'd have a perfect match, which would be almost suspicious. In fact, so yeah, I guess it would be cause for concern, but in practice, yeah, you're looking for like how close they look on the line to gauge performance. So this is useful because you can see like how well the model's doing across the whole range of data. So if the model has a good fit, then you're expecting, you know, the errors to be dispersed randomly either side of this line. You might see, you know, a range of the actual values where, you know, the model has potentially a bias if it systematically underpredicts or overpredicts for certain ranges. You might even detect ranges where the model performs, yeah, better or worse at say points. So if it's like accurate for lower values but not so accurate for higher values. And all of this is coming from, you know, a visualization rather than a simple summary statistic or a table of data. And indeed, yeah, this kind of thing is also quite useful for like communicating the performance of a model to others, because it gives like a more intuitive sense of accuracy than just trying to explain what the derivation of mean squared error is and things like these. So yeah, these predicted versus actual plots, very useful for like highlighting discrepancies and trends in predictions, showing us, you know, what things are hard to see in simple statistics. The next thing that I'm going to cover is residual plots. So these are kind of similar in that they show like the error for each individual data point. So this is the difference between the actual and the predicted. So this kind of what we're looking for is the horizontal distance between each point and the zero line. Typically, yeah, we're going to plot residuals on the y-axis versus predicted values on the x-axis. And in a well-fitting model, we're assuming that these are going to like be distributed randomly around the 0 point. That's the ideal. That randomness, if it's present, that randomness means that the models, you know, captured the main predictors and systemic patterns in the data, and kind of what's left is just unexplained noise. So typically, we'd you know, expect to see yeah, these just distributed either side there. Now, if we don't see that kind of random distribution, we can infer something about the model. So, you know, we can see here that in this case, that these do appear to be like fairly randomly distributed. But you know, for this top line here, as the prediction values increase beyond 30, then the predicted values seem to be a bit higher than the actuals. I guess because it's actual minus predicted, so negative value means that the predicted is higher. Yeah, so the model's under predicting, sorry. So that might be something we want to investigate. Now, without sort of digging into the data, it's hard to see why that might be the case, but it gives you a clue that you might want to investigate that a little further. It might be, you know, as a recording issue. Might be that this just because most of the data points are around this point here, that the model's just not got enough observations here. There's a lot of things it could be, but it would be something you might want to look into in a bit more detail. Yeah, so the other thing that these residual plots allow us to do is check whether there's any heteroscedasticity in the data. So typically, this we would hope that the residuals have roughly constant variance across the x as the x-axis increases or decreases. But what we can see with a lot of data, a lot of models, is that either the variance increases or possibly even decreases as x goes up. Now, in that scenario, it doesn't necessarily bias your model, but it might be that if you're fitting a parametric model, it may be that your standard errors aren't correct or at least aren't efficient. In that scenario, I guess you might want to consider some heteroscedasticity robust standard errors or some other means of doing that, possibly data transformation. Lots of things you can do there, but yeah, that's a typical way of picking this up would be by a residual plot. It's also possible to look for outliers, yes, on these kind of things as well. So if there's like a large residual at some point, that might be indicative of an outlier. And yeah, this could be a point that distorts your model or needs to investigate further. So in summary, yes, again, this is like a similar to the predictive versus actual plot in that you can get a feel for how well your model fits the data and whether or not there are any kind of like systemic biases in the model, whether it underpredicts or overpredicts. And we can use these residuals to kind of help us evaluate the model accuracy and guide any improvements to the models. Move on. Another thing that we can do with these residual plots is to look at influential points. So these are points where the point has both a high residual and a high degree of what's called leverage. So this is an observation with extreme values, just a case where either the outcome or the inputs are much larger or much smaller than the average. And the reason that these points are useful to look at is that they can have a disproportionate effect on your model. Doesn't necessarily have to be doesn't necessarily have to be a linear model, I suppose, but this is something that can like disproportionately affect the model. So yeah, a combination of a high residual, a large residual, and it being a high leverage point with extreme values can make it influential. So it's useful to kind of identify these if we want to look at them in more detail. One useful way of doing that is to look at what's called Cook's distance, which is a kind of a statistic that identifies these points. You can have included some code here, which relates to the previous example, but illustrates the point. And these you can compute these fairly easily using the function Cook's.distance, which is in the stats package. So it's included in base R. So here I've taken the residual plot and then just given a color code according to whether Cook's distance is greater than or less than 1. So when it's greater than 1, it's a high influential point, less than. So hopefully that's not too small on the screen, but you can see that the bluer points are the higher influential points. So these tend to be the ones where there's the residuals are high and also predictor variable or outcome variables are also high. This is a data set of deaths due to COVID-19. These data points, I dug into them a little bit. They largely just seem to be cases where it's a feature of the data set where that particular line represents a large population. So one of these points is all of England, for example, or Los Angeles, which are obviously very populous areas. And sometimes, yeah, there's issues. Sometimes that particular data set also had issues where the number of recovered cases was sometimes poorly recorded. So again, there's probably a data input issue. But all of that, stemmed from these things being flagged as potential points of potential influential points. So any residual analysis is not only is useful just to look at the size of the residuals, it's also useful to look for influential points as well. I'll move on to the use of visualization for comparing models. So it is particularly for communicating the difference between models to non-technical people. It's sometimes just quite nice to visualize things like R-squared and information criterion measures for each model. So here's a simple example from the previous version of this chapter where we're just comparing information criterion for the various Cohort models and the R-squared value there as well. So you can quite quickly see, which model is maybe preferred, having the lowest ERC value and the highest R-squared. Now differences in models, obviously could reflect differences in model specification or particular hyperparameters or indeed any other model property. So if you wanted to amend things with models, just run through a number of different combinations of possible choices, it's then relatively easy to plot these out and quickly identify what are the pros and cons of each approach. And then it's also, you can create some quite attractive visualizations for faceting, like say, in the book, there's an example of meningitis death rates. It's quite easy to split this out by country, so you can quickly compare how well the model does for various subsplits of the data set. So we can see here that the difference between the observed and predicted rates differs by country. So the Malawian one is not a great. It's just a straight line, so it's not a great. Definitely not a great fit. Might be I guess an issue with the number of observations there, but worth digging into anyway. Some models lend themselves more to particular visualizations than others. So there's an example in the chapter for using a decision tree model that shows how you can plot this out with rpartplot, which is a lovely little library for doing these things. I've used it before; it's great. So this decision tree diagram, well, it essentially visualizes the decision tree, so it shows the split criterion at each point, and then to yes and no, splits into yes and no there. And then you can relatively easily follow through the groupings at each stage, and you get to the outcomes down here at the bottom, which is, in this case, it's a class prediction, yes or no. Now I've done this before. It's quite a nice way of modeling what is, potentially a complex algorithm for non-technical people, because we've all seen a decision, something like a decision tree or a flow chart before, and it also teases out the main or the important thresholds and variables that are of interest. So whilst it's important to remember that these aren't necessarily causal, it does give you a kind of a hint as to which are the variables and indeed the thresholds, which are the most the most closely correlated, I guess we'd say, with outcomes. Yeah, I guess the main point here is, we can use these kind of visualizations as a way of taking a model which it could be quite complex to explain, and is a little bit of I guess, possibly like can be seen as like a black box, a model, and then we take the results and we can present them in a nice form which is easily intuitive for people. For other models, there might be similar visual aids. So this is an example of a variable importance plot from a random forest model in the chapter. And what this is showing is this is giving us a ranked list, bar chart form of features according to their influence on the model. So essentially, this is how much each feature helps reduce uncertainty in the model, and it gives then a ranking of importance. So if you are finding there are elements right down at the bottom that have little importance, you could potentially consider dropping them if they were onerous to collect, or you wanted to simplify the model. Equally, this also gives you a sense of which of them, like the key things that may be worth well, not only retaining but also digging into and possibly considering for future models as well. So in this case, we can see that there are like we can see the key variables at the top, which also correspond to the decision tree model up here in the main. And these can then, once you have identified which are the key variables, these can then be, you can then go to, like, say if you were discussing this model with a group of clinicians, you can go take that to the clinicians and then confirm whether or not that fits with their clinical experience, whether or not there are further things that you should be aware of, or factors that correlate with those variables when you to improve future runs of of future accuracy in future runs of the model. So yeah, this is all, I guess, really about where we focus our attention. So yeah, these are like the key variables. We can flag that up both in the results, but also if we are like talking to subject matter experts to get a better better understanding of the underlying phenomena for ourselves. Okay, I'll move on to ROC plots. So these are these ROC plots, which is short for receiver operating characteristic, which is a weird name, but the derivation is to do with radar systems in the Second World War. And then it was picked up, and these things are used more generally now for measuring, yeah, the kind of trade-off between sensitivity and specificity. So essentially, this is a way to evaluate a model across, differing thresholds or differing hyperparameters. So if you have a model where you have an element of choice in whether or not how you set it up. So typically that might be a threshold at which you consider the value to be a yes or a no, or something similar like that. Whether or not the value which you set that threshold obviously affects the number of true false positives, and the number of negatives that get incorrectly classified as true as well. So there's a trade-off there in that you want to avoid cases where the model fails to flag cases which should be flagged either as false positives or true negatives. What this does is what this curve does is that every point on the curve is like a different threshold value. And then what we're doing is then plotting the sensitivity rate, true positive rate, against 1 minus specificity, which is the false positive rate here. So because we've got a trade-off with this is essentially a frontier. So we can have a model that is somewhere on the frontier, but we can't have a model that's outside of it. And we can have a model that's inside of it, but it's probably not as good. It's not as good as one that will be on the frontier. We could improve it without cost. So having generated that curve, yeah, we can pick a point on it. Ideally, we want a model, closer to the top left as possible. So we identify all positive cases correctly, and so all negative cases directly. That would be up there as one, and then cases where we are 0.5 here are no better than chance. That would be, I guess, a bad model. Now, the overall quality of the model can be measured by something called area under the curve, which is correspond to this area here underneath the curve. And that gets higher, of course, as the curve moves up towards the top left. So more of the graph is under the curve. Now, if you have AUC, sorry, under 1, AUC of 1 would be perfect prediction when we're at that 1 up there, and then like 0.5 would be the bit on this dash. This dash diagonal line. You can generate these ROC curves using the yardstick or PROC package. The CRAN task view for machine learning also recommends the ROC-R package, which I've not used, but presume must be at least okay to have been included in the task view. So yeah, these things that are worthwhile looking into to, so you can make your threshold selection um, accordingly. Now, where you go on the curve, I guess, depends on the context. Um, so for something like, I don't know, if you were trying to predict a particularly nasty disease, then you may want to select a threshold where you minimize the number of cases where you fail to catch um, yeah, fail to catch um, fail to catch infections, even if that means that you pick up a lot of false positives. Um, if you have a case where over treatment has significant costs, then you would do, I guess you might go the reverse way because you want to avoid those false positives where people are treated when they don't necessarily need to be. And then the final thing to mention about RC plots is, again, these are ways of predicting, ways of evaluating models. So if you do have a selection of models that you're picking from, then you can plot these side by side. And again, that's what you're aiming to pick the model which has the higher area under the curve closer to the top left. Okay, just zoom that out a little bit. So the last particular visualization that we're going to discuss is the partial dependence plot, or PDP. And these are plots that aim to answer the question of how the overall prediction changes when a individual input changes, holding everything else constant. So we're just aiming to isolate the effect of a change in one particular input to the model here. Um, Now that gives us, I guess, a clearer picture of how one particular input tends to drive predictions, abstracting away from the effects of everything else. So I guess it's like conceptually similar to the partial derivative of a function, if you get the effect of that particular variable on the overall function's output. So how these work is that the feature of interest is varied, and then the other inputs to the model are held constant, usually at average values. And then for like each possible value of the feature of interest is entered in, and then we get like the average of predictions for that. Plotting these gives like a curve that visualizes the relationship between that particular feature and the predicted outcome. So in the book example, it looks at max stenosis by area. And here we can see that the marginal effect appears to have a sharp increase or sharp effect on the prediction value after a value of 50. And therefore, and after, and then sort of starts to tail off after that. So increases above 80 don't seem to have that much effect on the predicted outcome. And that kind of insight, so you have so that shows us we have possibly a particular threshold below which there isn't much of an impact, and above which risk is probably satiated, so there isn't like much additional impact beyond a certain point as well. So it tells us, I guess, that whilst some a value at a certain point could be dangerous, but after that point, then risk isn't necessarily increased all that much. So I guess it's important to note, there are like some limitations and considerations when you're looking at these kind of things. So what we're doing here is we're isolating the effect of um, one particular variable, and holding everything else constant. But of course, in the real world, very rarely is the case that everything else is constant. So whilst this particular variable changes, it might be that it's correlated with other variables, and that therefore, like, assuming everything else is constant is not an assumption which is yeah, which is realistic. And then, of course, in practice, the other thing I guess to mention is that whilst this maybe to an average, like if you're then applying this to an individual case, there are many other factors that you would have to bear in mind. So it's not the case that this particular partial independence plot might not uh, reflect all those individual nuances in individual cases. So overall, whilst these partial independence plots are useful for interpreting feature effects, we might want to use them with caution, just because the assumption you're making is quite strong. Okay, I'm going to wrap up there, I guess. So to kind of draw this together a little bit, I think we can probably say that visualizing model results, are firstly a very useful part of building a model. So we've seen that plotting predicted and actual values together can immediately give us a feel for the overall accuracy of the model, and some indications of any bias, if there are any biases, if there are any in the model. We've also seen that plotting residuals can be a useful thing to do to expose like patterns where a model might be underfitting, overfitting, misspecified, or whether there are issues like heteroscedasticity that we might want to deal with in the model. We also looked a little bit about how plots can show us influential points in the data set that may be worth looking into in more detail to see if they're true outliers, or whether we want to consider them in the data set at all. We also talked a little bit about these visualizations being useful for communicating features of a model and outputs in the model to non-technical stakeholders. And then finally, there are some visualizations like ROC curves, partial independence plots, which allow us to further tune the model and dig into like the finer points of how we interpret the kind of more detailed or granular aspects of the model to optimize accuracy. So the common thread through all these things is that visualizations are a much more effective way of doing this, or certainly more accessible way of doing this than just dealing with code or tabular data, particularly for non-technical people. So when you're doing these sorts of analyses, they're very much integral, I guess, to doing good quality analytical work, and a powerful way of making sure that you have the best model that you can get, I guess. Okay, so that was me. I'll stop there and ask any questions, and we can discuss that.